my name is Liv. I'm a PhD student at Imperial College in London. I'm going to talk about accelerating graph building for particle tracking. So I'm going to actually just skip all the theory of graph neural nets and why it's needed for tracking and why tracking is going to take long, because I think we've seen that by now, and we're happy with that. So kind of, yeah, as you know, tracking is going to need to be sped up quite a lot. Graph neural nets are showing great promise. Graph building is a little bit of an issue. It can be quite slow. So I've been looking specifically at ways of accelerating graph building, and I've been doing that by taking a kind of a reinforcement learning approach. So to go into a little bit more depth of why graph building is slow, you do create kind of a lot of edges. It can take a lot of time, especially at low PT cuts. You can see kind of a quick timing test there, and that's for kind of the baseline exit track. Also and now again, I'm speaking for the baseline exit track. I know there's a lot of work that addresses these issues, but graph building also sometimes has assumptions like you can only have one hit per layer, you can't have missing hits, or you remove kind of noise hits or stuff like that. So those are obviously assumptions we don't want. So I have been thinking about reinforcement learning for this problem. And the reason I think reinforcement learning could be a good candidate is because sometimes with various graph building methods, you build a big graph and then you try to prune it or make it smaller, or you have some clever physics way of removing the edges. But maybe you could just build a graph that didn't have those bad edges in the first place. So as you might know, reinforcement learning kind of has an agent that acts in an environment. And maybe you could have that agent kind of almost build a track. So that could maybe build smaller graphs. If it has a good idea of where it's going to go, then maybe that would give you a smaller graph. And if you use kind of an RZ kind of space, most tracks should be a straight line. So that should be fairly easy for a reinforcement learning agent to learn. You could also take advantage of various physics information. It should be parallelizable since each track is independent. It naturally also addresses like these limitations here. And even shared hits wouldn't really be a problem because you could just kind of keep the tracks in the detector and the agent could just go where it thought it was right. And even if you start seeing kind of things that are unphysical or things you don't want, in reinforcement learning, you set a reward, so you could start punishing kind of bad behavior that you didn't want. So in theory, it could potentially be a good solution. Since reinforcement learning isn't maybe quite standard and hep yet, I'm going to take a few minutes just to talk a little bit about reinforcement learning in general. So in general, you have this sort of structure. You have an environment, you have an agent acting in that environment. Based on his actions, it will get a reward. The agent will act according to a policy, which you learn. It's typically a neural net. So you learn kind of, given this certain state, what should I do next? You typically also have a value function, and the value function is a metric of how good is the policy or how good is the state that I'm in. It doesn't have to be a neural net. It can be. It can also kind of just be some function. So that's the general structure. There's lots of different reinforcement learning algorithms. The two main types are model-free and model-based. So in model-based, you have some sort of kind of ground truth model of your environment. A good example here is, you probably have heard of AlphaZero. So for instance, if you have chess, you need a model of chess. You need to know kind of what are the allowed actions and stuff like that. The other one is model-free, when you don't have a model of your environment, at least not such a detailed one. And model-based methods are usually more sample efficient, so you kind of more quickly learn the thing you're going to learn, but they usually take more time to develop because you need that very good kind of model of your environment. So within model-free, You have kind of two main approaches. One is a policy optimization, and that's when you try to learn the very best policy. So you that's what you're optimizing for, the policy that learns which actions to take. The other one is Q learning. So Q learning actually tries to assign a quality to each action. So it's a slightly different approach. There have been, you've probably heard of reinforcement learning. It's been quite successful in recent years. It's been used for playing games like chess or AlphaGo or stuff like that, or for walking robots. There's a little animation there, but that doesn't work. And quite recently, there's been some good success with controlling asthma as well. So if you're thinking, oh, is reinforcement learning applicable to my problem? There are some things to think about. Usually you would want the environment to be intractable. So you wouldn't want to be able to just solve it analytically, because if you can do that, that is usually better. You would also need to have some sort of environment where your agent receives some sort of reward based on its actions. And you would need the environment to kind of change based on what your reinforcement agent is doing. Most reinforcement learning models also assume Markovian states. So it assumes that where I'm going to go next only depends on the state I'm in right now. There are some exceptions, but that's the general rule. So before I kind of started trying to apply this, I had a little look at how good would my reinforcement agent need to be. Sorry, this is quite difficult to read off. Yeah, what I tried to do is that I had a look at, again, using the kind of the standard exit track graph building. What's the distance between the true hits and the fake edge hits? So kind of how far away are we from the actual hits? And what I saw was that kind of independent of PT, if I managed to get a reinforcement learning agent within kind of 20 centimeters of the correct hits, then that would cut away 25% of the fake edges, or for 10%, it would cut away kind of 50% of the fake edges. So it shows that even if I have a reinforcement agent which isn't perfect, that would still be helpful. So to describe a bit how I approach this, I started with a seed. And in reinforcement learning, you also need a state. So I played around with kind of a few different states, but usually I describe the state by the position of the hit, and usually also some sort of information about the previous state, just to kind of make it Markovian. So I start with a seed. So the way I do that is I kind of sort the hits in the RZ space, because most hits would go regularly outwards. And I just use the two first hits in a track. So I do use the truth level information there. And then I find kind of the change in R and Z for that hit connection. And then I do something a little bit strange that I'll explain in a minute. I assume that the next position is going to be the previous position plus that same change in R and Z. And the reinforcement learning learns a correction to that assumption. So I'll explain why I do that in a second. The reward is then the distance, like the negative distance between the correct hits and the prediction. So the closer it is, the higher the reward. Then it continues until n hits are found. So that's just some arbitrary number that I set. For this, I use kind of a vanilla policy gradient. So as you can hear from the name, is the most basic reinforcement learning you can use. But it's quite maybe easy to see what's going on in this sort of approach. And it's quite standard to kind of start a workflow with something like this. So the way that works is that you collect a set of trajectories by running the policy, you compute the rewards, and you compute your advantage estimates, which is that kind of value function. You estimate your policy gradient, and then you kind of learn this policy. So there's different ways of doing it, but the approach that I took, you essentially learn a Gaussian distribution. So you sample so in each state is associated to a Gaussian, and you sample your actions from that Gaussian. And as you're learning, you kind of the standard deviation of that Gaussian decreases as you learn which actions you should take. So I want to take a few seconds just to talk about inductive bias a little bit. For those of you who were at the Learning to Discover workshop, there was lots of good talks on this topic, and I think it's quite important to something like this. So inductive bias is really what makes machine learning favor one model over the other. So I like to think of it like as if you try to teach someone to, say, surf who've never surfed before, there's a lot of things they wouldn't do because they know intuitively. They know that, you go on top of the board, not under it. They wouldn't, do a headstand on the board. Like, there's a lot of action space that's already eliminated. If you try to do the same with a reinforcement learning agent, it wouldn't know those things. It has no intuition, so it would be able to explore all of that action space. So you can really kind of take advantage of inductive bias and try to infuse your model with some sort of knowledge that you have about the situation. So an example here is, this is an example of one of my reinforcement learning agents training. If I try to naively just predict the position, so that would be, given the state, what's the position of the next hit? That never learns anything. It does really badly under the conditions I've given it. And the reason for that is that there's so much action space. It could be really anywhere, so it does take a very, very long time to learn. And I would probably really need to improve my environment, maybe do a more complicated model if I wanted to do that well. Instead, what I can do is that I could use some of my intuition for the problem and say, okay, the hit that's going to come next is actually going to be quite close to the previous hit. It's not going to be on the opposite side of the detector. So I could just predict the change in position instead, because that's going to be much more consistent, and it's going to be easier to predict. And then you can see this kind of orange line here, so that is actually starting to learn something. I could even take it one level further in abstraction and say, I'm going to assume this drdz is going to be quite similar to the previous one, and I'm going to learn a correction to it. And that's this green line. So you can see that improves even a little bit further. They do kind of end up in a quite similar place. Another way to take advantage of kind of the symmetries of the problem is that you can also take advantage of the symmetry in the Z space. So you can reflect along this kind of R axis here. And that eliminates half of your action space. So you can see kind of that also improves the performance. There are some situations where you might not want to do that because you want to conserve kind of a difference between the negative and the positive Z space, but you can take advantage of it. All right, so how does it do? Here is a little animation. I should say, so I'm using two truth level hits. So the two first hits are the truth level, and then it predicts 5 hits after that. This is the beginning of it learning. So in each iteration here, it's kind of starting to begin to learn what to do. This is a curve showing the number of steps and the average return. So with the average return here, what it's showing is the return for the whole episode. So that episode is then trying to predict 5 hits. So when we have, for instance, an average return of minus 150, that means that for those 5 hits, that's the average return. So it's still quite far away from what we want. It is starting to learn. If I leave this for a long time, it does go a little bit higher, but then it saturates about 100 or something like that. So that is still like, let's say 20 centimeters consistently away from the hit where we want it. So I tried something different. I tried to take a slightly different approach. It does seem to learn something, but it's not quite good enough. So I tried Q learning. So in this previous example, I've been using continuous states. So my reinforcement learning, predicts continuous values. So I tried Q learning instead. This is where you don't have a continuous action space, you have a discrete action space. A kind of a simple example, so you can do Q learning without machine learning, and you can do it with machine learning. A very simple example is if you kind of enumerate all the different states and actions, And then you actually explore all of your action space and you learn the quality of each action given each state, just analytically. And the kind of neural net approach that would be to say that, okay, I don't actually need to enumerate all the states because maybe there's too many states. So you use a neural net to learn a quality function instead of enumerating all the possibilities. Classical example, if you've ever looked at this before, you've probably seen this example, would be kind of a taxi driving around a very simple grid, dropping off and picking up passengers. And then you can kind of have actions for each of those. So I tried a deep queue, so kind of a deep neural net approach to this. And the way I tried to discretize the space was that I used the modules instead. So I tried to say, okay, maybe it's difficult to predict the continuous numbers. I'm going to try and predict which module it's going to go to given the module it was in. It doesn't do well at all. So it's all over the place. I think I'm still not quite done with it. I think maybe I can make it work, but it doesn't seem like the most promising direction. So I tried something else. Again, kind of trying to use this inductive bias thing, trying to help it a bit, because when it's predicting now, it is actually predicting a lot of places that aren't even in the layers. So it's obviously unphysical that you would have a hit that's outside the layers. There's stuff like that that I wanted to mitigate. So I tried two different methods. One was I tried to use the seed that I had to predict the next intersection points with the layers. And that would kind of be the basis. The other one was kind of a bit inspired by the module map work, but I still wanted to take advantage of the fact that you're kind of almost building a track as you go. So I created a module map, but the module map was also indexed by the slope parameters. So my thinking there was that, let's say this module here, it could, in a module map, be connected to something over here, but you know that if it's associated with this seed, it wouldn't be likely to go over there. So you have a module map that kind of, has that slope information in it. So I tried to use those two methods combined with reinforcement learning. Before we look at the reinforcement learning, I just want to show how well that does for graph building without any reinforcement learning, because I wanted to see that I didn't lose any efficiency or anything like that using those methods. So here are some of those results. The blue here is the original, again, that's the kind of extra track. And then you see the other methods here. So you can see that those two methods still have a fairly high efficiency. They do have an improved purity, which is what you want. So you see that even without any reinforcement learning, using something like that does increase the purity of the graph. The number of edges isn't too different, except that kind of lower PT, then you see that you really get a nice effect with a lower amount of edges. For the number of nodes, maybe surprisingly, my methods actually are a bit higher. The reason for that is partially because there are some cuts in the original method that you wouldn't have here, like you could connect hits that are not in subsequent layers and stuff like that. One thing I should say is that these methods are quite slow at the moment because, well, there's different ways of doing it, but if you kind of say, okay, I think, you know, the hit is going to be here in this next layer, then you need to look for hits that are close to that value. And if you do that each time you propagate a track for each hit, that can be quite slow. So I tried to combine it with reinforcement learning. And the thing I saw was maybe a little bit surprising. So what I saw was that here you see no reinforcement learning. So this is literally just predicting the intersections that you would calculate analytically, which seems to actually do quite well. There are, of course, some issues, like sometimes it would predict a hit that wasn't there or something like that. And it's not very good at dealing with, like, if there's energy loss or something like that. But in general, it does quite well. With the reinforcement learning, it gets a little bit confused. It doesn't quite know what to do with it. So maybe it wasn't quite what I expected, but yeah, that's where we're at. I also, just out of interest, tried to see, okay, how well would it actually do if I didn't use the seed at all? Not well is the answer. It's doing a lot of weird things. But I think what it really goes to illustrate is that there's a lot of unphysical behavior that is allowed in this model. So I think maybe if I try to almost use this as a bit of a guide to eliminate some of that action space that shouldn't be allowed, maybe it would increase performance. So potential improvements. I think one main thing would be action masking. So that's the idea that you don't allow it to do actions that you know it shouldn't do. So you kind of take those options away. An important important difference here is that you can predict an illegal action and then correct for it. And that is something I have tried. But it's not quite the same because you lose that link between this is what I predicted and this is my reward for that prediction. So you kind of lose that link if you correct for it afterwards. So a better way is action masking, where you actually, let's say, so for instance, for this, you learn a Gaussian distribution, and then you sample from that Gaussian distribution. Instead of taking illegal samples, you could kind of just take away parts of that Gaussian distribution so it never samples from it. So that's something I think would improve it a bit. I have yet also to explore a lot of other reinforcement learning methods. I have tried DDPG, which is one of the more kind of advanced ones, but that one is known to be quite brittle, so that didn't go well. But there are some other things I could still explore. I think also including more physics restrictions, putting in more domain knowledge into this thing would probably help. And another thing that could be interesting would be to combine the reinforcement learning and the graph neural nets. So maybe have a shared loss function somehow. That's something that has been explored, even for particle tracking. So there was a good talk quite recently that you can have a look at if you want, that does that for a slightly simpler problem. But they got some interesting results from that. So that could also be interesting. So to conclude, we can see that the reinforcement learning does learn something. It's not quite as good as what we want, but there is something there. And I think in theory, there are some claims that you can make that it should in theory do better than module mapping because you are kind of propagating the track in the way you are. So I'll continue to explore it and see if I can make it better. Eventually, I will try to put something like this on an FPGA and see if I can accelerate it as well. Thanks.
Let's see, let's first start to see if there are questions on Zoom. I do not see the raised hands. Then I'll open the room for questions.
No, you go.
You go first.
Thanks so much. This is really, really cool. And thanks for being honest about when it worked and when it didn't work. Maybe I'm misunderstanding, but is the idea you have a seed doublet or whatever, and then that's your like starting state. And then is every subsequent step, is it using information? Like if it sees a hit in front of that doublet, is it using that information, or is it predicting all of the next 5 steps without any new information?
Yeah, that's a very good question. So I have tried different ways. I've tried one where it doesn't look at the actual hits. So that's a lot quicker, obviously, but yeah, so I've tried kind of just predicting the next state. And then, yeah, you're right, it wouldn't see any information for the next hit, but I've also tried kind of selecting from the hits that it sees, which sometimes performs better, but it is a lot slower because you need to kind of open that window and say, okay, these are the hits. But yeah, I've tried both.
And then, sorry, just to really quickly follow up, if it then finds the next hit, does it retain like a memory that now it's a triplet with that curvature, or is it purely like state to state and it forgets that it's a triplet, forgets that it's a quadruplet?
Yeah, good question. So Right now, it just forgets because I haven't encoded any information in that, but you so easily can. I mean, you know, change 2 numbers and then you can encode where it is in that. So I have tried that as well. But yeah, it's both things are possible.
Nice, Paulo.
So actually the thing I wanted to suggest was mentioned triplets. So I mean, you would have more information there to build your guess from. But the other thing I wanted to ask, because I'm completely ignorant of reinforcement learning, is the mechanics. So you have like mini batches of things you try together, and then you. I mean, how many tracks are you learning from before you change the policy, and does it make any difference?
Yeah, good question. So yeah, that is how you usually do it. You kind of when you learn the value function and the policy, you exactly as you say, you usually have a batch. I think right now I have quite a big batch number. I think I have like 4,000 tracks or something. So it would take quite some time before each update of the policy, because it needs to. I mean, every track is kind of different. So sorry, so you need to see quite a lot of examples.
I added a reference to your Q&A on this. It's actually the work of Benjamin.
Oh, thank you.
Yeah, on the surface prediction navigation for the track ML detector, where we did quite similar research, and we also fell in quite similar pitfalls. Particularly, and this is something we learned at the end of the entire endeavor, is yes, you can predict with a network. You can start learning it better and better, but at the end, and we should have done this thought at the very beginning, the inference on a network is usually high-dimensional matrix multiplication, while the intersection with the surface is a matrix intersection of rank 3 and is humongously faster. So usually you can try hundreds of surfaces with straight line intersections in the time you do one inference of a network. So a trial and error was actually the fastest we could do in the region. So it's quite funny, yeah.
Maybe it's a crazy thought. I mean, why not treat this as a game that you navigate from this seed and then see where this go, as node will be the option, right? The space point recorded in the event will be option. And then you have limited amount of choice. Let's say can you limit your choice to the option in the next layer to play like that.
Yeah, exactly. That is something I've thought about, and that is somewhat similar to the action masking. So you could have kind of these are the available hits, and that would be your available actions.
Exactly.
The only a little bit of a challenge in that is that each time you would have then very different actions. So it would be a little bit difficult to learn potentially, because you're trying, at least in this example, you're trying to learn some sort of Gaussian. And then you could take some values kind of away from that. But if that function is vastly different each time, it could be difficult to pick up on what is actually the things I should learn.
Yeah, but essentially those actions are limited due to the sensor positions in the checksum.
Yeah, that's true. I think maybe because of the combinatorics, it could be challenging. But yeah, I think there could be something there. Absolutely, yeah.
All right. Last question. Otherwise, make yourself pretty for the group photo. And we conclude the first part of this morning session with that. Thank you, everyone. And